Yeah, I'm going to be talking about Scalaz-Stream today, and I've got a lot of stuff I want to get to, so I'm pretty much just going to get right to it. So, okay, what is Scalaz-Stream? So, Scalaz-Stream is a library for doing stream processing and I/O. And sort of the goals of the library are that we want to write programs that do I/O in a compositional way. So we want to be able to assemble them from smaller pieces. And another sort of big goal of the library is we want to make it really easy to write code that is resource safe. So we want to make sure that file handles get closed, database connections get closed when they're supposed to, and so forth. And I guess sort of the origin of the project is, it sort of started as, some work that Runar and I did for the book. And, last year when I was up here talking about this stuff, this was somewhat theoretical vaporware or, prototype code that we had written for the book. And, but yeah, now it's actually a real library and you can use it for real things. And, hopefully this will pique people's interests and, they'll actually maybe try using it. So just by show of hands, how many people are using Scalaz-Stream now? Okay, not too many. All right. Well, all right. We'll see how this goes. So Scalaz-Stream it's based on the core data type of the library is this data type process. And so conceptually, process represents a stream of values. But it's sort of a special type of stream in that it may periodically sort of stop and wait for some external request to come back before it continues emitting values. So I'll kind of talk more about what that means in a minute, but sort of the simplest way of creating a process is we can just create a literal process that is going to emit, the values that we give it. So I can say process 1, 2, 3, and we can see it's just a process that's literally going to emit the values 1, 2, 3. Now process has two type parameters here. One is int, so that is the output type, the type of elements that the stream is going to be emitting. And this first type parameter is the request type. So if this were an effectful process that were making some external requests, we would see something else here besides nothing. The fact that it's nothing is just saying that this is a pure, just in-memory sequence. It's not executing any external requests or won't ever ask to execute those requests. So just a little bit of, just to make the slides a little shorter, I'm saying val p is equal to process. And so a lot of the operations that are defined on lists are also defined on processes. So I can append one process to the next. These are all just different ways of kind of writing a process that is just going to emit some values to the output. I can emit a single value. If I have a sequence, I can just emit all the elements of the sequence to the output. And you can see the result is pretty much what you would expect. Okay. And yeah, just to mention, so there's map, filter, fold. So I mean, all the operations you would expect, for lists are also defined on process. And yeah, these are just a few examples. If you are in the REPL, you have a process, do tab completion. You can see there's a whole bunch of functions. I'm not going to go over all of them here, but I mean, the idea is if it makes sense for a sequence, it probably makes sense for a process as well. Okay, so far I've just been talking about these pure sequences, which there's no I/O involved, so it's not very interesting. You're thinking, well, I could have done all these things with just regular Scala collections. So here's an example of our first effectful stream. So this process fizz is going to wake up every 3 seconds and emit the value fizz. And so a couple things to notice here. So one is the output type is string. So we're obviously emitting the string fizz. But now we can see this is no longer nothing, this is task. And task is, it's a data type from Scalaz. It's sort of a better I/O that handles binding to asynchronous and parallel computations, and also has some good support for exception handling. I'm going to show some examples of task a little bit later. But this is just saying that, OK, waking up every 3 seconds, that's sort of, it's going to be a series of these asynchronous steps. We want to go to sleep, not literally by blocking the thread, but we want to schedule an asynchronous task to be run 3 seconds later, and we want to keep doing that. And we can see that just the representation of it is, it's no longer just emitting some values, it's this await. So a process is a state machine. It can be one of 3 states. It can be emitting values, it can be awaiting for the result of some request, or it could be halted. So it's done emitting values. And this is just to show that that effectful stream that I just created. I mean, I can still call take, I can still call filter, I can still call drop, I can still call those same functions on it. It doesn't matter that it's this effectful thing. And then just to kind of observe what's happening here. So here I'm using like an evil side effect to just print out the values that are emitted by the stream. And if I want to actually run this stream, so this is a conceptually, it's a program that is going to, when it is run, it's going to emit some values. So how do I actually run that stream and sort of get something out of it? So there's this function runLog, which takes a stream. It takes a stream, and it's going to sort of compile that down to a single monolithic task. And the task, the value of the task is just going to be the values that are emitted by the stream. And so nothing actually happens when I call runLog. This is really just, it's more of a process of compilation. It's converting from a stream to just a single monolithic task. And this is, so far, we haven't actually done anything. If we want to actually run that task and actually have that effect of waking up every 3 seconds, printing, and so forth, then we actually have to run the task. So we can call that task.run, and it's going to, after 3 seconds, print fizz, then print fizz again. And we've only taken the first 2 elements of the stream, so it's going to stop at that point. So the interesting thing about task is that so task does not represent a running computation. So task is a description of that entire process. Once we've compiled it, it's just a description of what needs to happen. So the task is not used up after you run it the first time. So this is sort of a major difference between task and the Scala concurrent future, where once it's computed, it's that's it. The value is cached, and you can't. If you run it again, you'll get the same value. And this, I think, is actually very important for compositionality, because what it means is you can separate the code that sort of produces the task from the code that chooses how to evaluate it. So if you wanted to add some retry logic after the fact to a task, that's very easy. You just write a general purpose function to do that. You can't really do that with the future. You have to embed sort of any retry logic into the future itself. So in general, it's just much nicer to work with these sort of pure first-class descriptions of what you want to happen. OK, so there's a number of operations on streams for combining streams in different ways. So obviously, we can operate on a stream with the usual sort of list operations, map, filter, all those sorts of things. But we can also combine multiple streams in various ways. And this is one example of how you can do that. So here we have buzz, which is going to wake up every 5 seconds and emit buzz. And I can say fizz buzz, which is fizz merge buzz. Now, the merge operation is conceptually what it's going to do is when either of its inputs has a value available, it is going to emit a value to the output. And you can see that if we actually run fizz-buzz, it's going to, at 3 seconds, 6 seconds, and 9 seconds, it's emitting fizz, but then it's interleaving buzz at 5 seconds and 10 seconds. And so this is sort of this is sort of arbitrary non-determinism. You're allowing sort of arbitrary interleaving of these two streams. But you could very easily write sort of a more bounded merge, like, okay, merge these two streams, but make sure that one does not get more than, say, 10 elements ahead of the other. And it's very easy to write those sorts of policies in Scalaz-Stream itself. And they're just sort of these generic combinators that you can reuse wherever you want to. Just like if you write something that does both a map and a filter at the same time. I mean, that's just a generic function that you can reuse. Okay. And if you want to see a bunch of examples of some of the functions that are already in Scalaz-Stream, so there's various deterministic functions for combining two streams in the T module. There's various non-deterministic functions for combining streams in the Y module. And there's various functions for sort of transforming in some stateful way, possibly individual stream in process one. And yeah, I'm not going to try to go over all these, but just lots of different functions there. Okay, so that is the basic programming model, I guess, of the library. So it's it's a very nice model. I think it's familiar to people from working with lists and sequences and so forth. And so the next sort of question is like, okay, this sounds great, but how do I actually bind this this API to talk to external sources? And so Scalaz-Stream has a few different ways of doing that. So I'm going to try to show a few of them here. So one is there's a few functions in Scalaz-Stream IO which have just different ways of creating streams from IO-based sources. So we can create a stream from the lines of a file. And you can see the output type is string, and the effect type is task, implying that this is going to be doing some I/O. We can again call take and take while. We can call the same operations as on pure streams. And you can see when I actually run this, this is actually going and fetching the lines of this file and returning that as a vector. Now, what's interesting about this stream is that this is actually encapsulating the full life cycle of working with the file. So this is not, the consumer of the stream is not responsible for making sure that the file handle gets closed. When the consumer of the stream is finished, the file handle will be closed. Even if that consumer ends up throwing an exception, we still are always going to guarantee that that file is closed. So this is sort of a nicer model than sort of traditional I/O, where it's like every user of a resource is responsible for ensuring resource safety. And the type system doesn't really provide any help. If you forget to close a file, I mean, it's just going to be potentially a runtime error or a resource leak. This is sort of like we're encapsulating all that logic in one stream object. So just to give a sense for how this works and how you can kind of build this type of resource safety into the streams that you construct. So there's this function on process called onComplete, and it works a little bit like append in that it's going to run the first process and then the second process. But unlike append, it is guaranteed that you're going to run that second process, even if this first one finishes with an error. So here I'm just using a side effect I'm printing cleanup, but you can imagine doing some real cleanup in there. And you can see if I say lines, take two, run log run, and then you can see that that cleanup action is being run. And notice this we get that cleanup action even though we only took the first 2 lines of the file. So we didn't have to traverse to the end of the file and then have some magic cleanup action get run as a side effect. We're allowed to terminate early. We don't sort of break resource safety if we terminate early. Another thing is that if we have exceptions that get thrown while we're processing the stream, we also still call the cleanup action. So here we're calling, so let's go back to the input here. So you can see the first line of the file is this comment. So it's not actually a double. So if we're calling map to double on all the lines of the file, this is going to bomb with an exception. And so you can see when we actually run this, the cleanup action still gets run, and then we just re-raise the error. So if you want, you can actually catch the error within the stream and then recover from it. But yeah, I mean, this is just to show that, OK, you can sort of program as if you didn't have to worry about exceptions. And unless you need to do something different to handle those exceptions, everything just sort of works out, which I think is very nice and a lot less error prone than doing these things manually. OK, so that all sounds really good. So what about when you have to bind to some asynchronous or side effecting sources? So this is very common. I mean, when you use Scalaz-Stream or any sort of functional approach, I mean, you don't control the entire universe. You can't really ensure that. Sometimes you just have to interface with some API that is a little bit more side effecting or just has various nasty stuff that you just kind of have to figure out a way to talk to. So Scalaz-Stream has a number of ways of binding to those types of APIs so that you can. You have sort of the nasty imperative API on one side, and then on the other side, you get this nice stream abstraction for working with it. So I'm going to cover a few different ways of doing that. So one is, so task, I mentioned, has very good support for binding to asynchronous computations. So kind of the simplest way to create a stream is by creating a task and then wrapping that in a stream. So here's an example of a callbacky API. So we have this function read. So read is not going to return an array of byte. Read is taking this callback that it will then invoke at some later time with either the error or the array of bytes that it read. Now, then this is kind of a common type of API, and maybe if we were using Node.js, we'd call ourselves good and just go ahead and program directly with this model. But I actually think this is a kind of a horrible model to have to program with directly. We really want to have this nicer abstraction of having this thing that sort of, at least the API feels like it's a blocking API, even if under the covers it's doing all this asynchronous stuff. So I can take this read function and I can say task.async, and I pass in the read function, and sort of as if by magic, that becomes a task array byte. And this is a monad. I can map, flat map, and sort of do all the typical operations here. And yeah, I mean, the type, if you just sort of follow the types of async, it just sort of works out. It's a little bit brain bending if you actually look at it. But yeah, this sort of lets you sort of invert control, and you get this nice sort of straightforward API from this callbacky one. Sometimes you have a callbacky API where you have sort of two continuations, a success one and a failure one. But it's you still just use task async, and works a little bit differently, but it's the same sort of idea. One interesting thing about task is by default, when you flat map a task, it is going to run the flat mapped function in the same thread as whatever the sort of original callback gets invoked in. So if you want to if you don't want that behavior, you can fork off a new task for the rest of the computation. So by default, task is not going to be going through a thread pool submit cycle every time you flat map over it. So that can be very good for the efficiency. OK, so now that I have this task, how do I actually promote that to a stream? So there's a function on the process object, eval. It's not even specific to task. You can promote any effect to a stream. And yeah, I take that task array byte, I call eval, and I get back a process of array byte. And this is a process that's just going to await the result of that task and then emit it and then stop. If I wanted to run a task repeatedly, I could just call that stream.repeat. Repeat is just another generic function in Scalaz-Stream that just is going to run that stream over and over again. OK, so that's kind of the most idiomatic way of binding to an asynchronous computation. It's best if you can bind at the sort of earliest possible stage. But sometimes that's not always possible. Sometimes you have some process that is just going to be pushing you values, a stream of them. You don't have access to the asynchronous task corresponding to a single element of the stream. So in that case, you can use something like these asynchronous queues. So here I'm declaring, I'm importing Scalaz-Stream async. I can say queue of in. And I actually get back two things. So queue is going to be this mutable. It's this very side-effecting mutable API that thread 1 in the imperative programming world can go ahead and populate by calling enqueue multiple times and by calling close. It can also call fail to raise an asynchronous exception. And then meanwhile, on the other side, in sort of the other side of the universe, the stream processing world here, source is going to be just a regular process of the values in that that are put into that queue asynchronously. And this queue is not blocking, so there's no there's no actual blocking reads anywhere. It's actually this process will just be woken up essentially whenever thread 1 enqueues a value to it. So it's all sort of non-blocking like you would expect. OK, and then finally, the last way I'm going to mention is a lot of times you have some asynchronous signal. So it's a continuous value that is being updated by some external process. And the way that you can bind to that is you can declare this async.signal Boolean, and you can get two different types of streams out of a signal. So one is you can just get the sort of continuous version of the stream, which is it's always going to be defined. Whatever the current value is, it's going to return that. And the other option is you can get a discrete stream, which only is going to emit a value when the signal is changed. So using this API, you can have thread 1, which is setting the value of that signal. And then meanwhile, in thread 2, you can just react to any changes to that signal, and you get this sort of nice stream processing abstraction. So, and there's a few. I was going to talk about binding to actors, but I'm going to skip this, but I will possibly come back to it during the Q&A if people are interested. But yeah, so those are all just different ways of binding to some asynchronous API. Now, yeah, I just wanted to mention for credits. So Runar and I, we worked on a lot of this stuff for the book. A lot of this work was based on some work that Ed Kmet did in Haskell, this library machines. And then also wanted to give a shout out to Pavel, he's at this company Spinoko, and they've been actually helping sponsor some of the development on this. And if you're interested to learn more, you can check out chapters 13 and 15 of the book, which we're actually told by the publisher it's looking like a June publication date. So it's actually finally going to be on bookshelves, which is good. And
Are those chapters in the latest download?
yep, yeah. So all of the book chapters are in the MEEP right now. So yeah, all the content is there, you know. And yeah, this is the GitHub page if you want to check it out. We've had a number of people contributing to the library, which I think is awesome. And yeah, I'm not going to try to mention all the contributors, but you know, even stuff as simple as just, oh, I added you know, this little stream transducer for doing this little task that was useful. There's just lots of little functions that are very generic that you can write that are helpful. So yeah, that's all I got. So any questions? Yes.
So I see some
Yeah, a little bit. So I guess, I mean, a lot of these libraries are, oh, repeat the question. So contrast this with the observable or RxJava stuff. So yeah, a lot of these libraries are similar. I think it's one of these things where the devil's in the details. The thing I don't like about Rx, like the RxJava representation, is basically the entire stream is asynchronous. So it's like a very push, the entire stream is push. And that works out well when you're just operating on one stream at a time, but as soon as you want to do some like, you know, you want to do like a merge where you're, yeah, where you basically need that sort of pull type of API, and then that representation doesn't work out as well.
they do have a merge.
Three together?
Yeah. Oh, so yeah, the question was, could you combine all of these different types of effects, really, or ways of getting data into a single computation? And yeah, definitely. Yeah, there's nothing restricting you from doing that. Yes. Yeah, it's basically that because task is not a running computation, you can bind to it multiple times, and it's just going to rerun the computation. Yeah. So, so yeah, the question is, how do you deal with sort of queue sizes and back pressure and that sort of thing? So I guess my general answer is start with. So the Scalaz-Stream answer is you start with a fully deterministic computation model. So if you start with that, it's very easy to ensure you know, deterministic memory usage. And then yeah, when you bind to something external, you know, that's why I was saying you really want to bind to the task that's fetching individual elements, because that's what's going to give you complete control over queuing and memory usage. And yeah, if you can't do that, then you know you have to implement some ad hoc way of doing back pressure or something. And there are like the queue, you can you know, you can get the current size and you can do things like that. But yeah, it sort of feels somewhat ad hoc to me. But I think it's sort of the best you can do. So, but yeah, feel free to come talk to me after. Or I don't know, should I just wrap up here? Or? All right, thanks everybody.